Okay, so it is time for the last but not least paper of this session, which is last paper is entitled "On the Impact of Different Voltage Unbalance Metrics in Distribution System Optimization," which is going to be presented by Kshitij Girigoudar, who received his bachelor degree in electrical and electronics engineering in India and master science degree in electrical power engineering from Aachen, Germany. Currently, he's a PhD student working in the department ACE department at the University of Wisconsin Madison. His research focuses on modeling, optimization, and control of distribution systems of integration of renewable energy generation. So, Kshitij, please present your paper. Thanks.
Thank you for the introduction, Jose. Can you see my screen?
Yeah, perfect. Okay, nice.
Yeah, great. Hello, everyone. Today, I'm going to be talking about the work that we did on the impact of different voltage unbalance metrics in distribution system optimization. This was a work that was done as part of a project funded by DOE's Solar Energy Technologies Office. I'll start off by introducing voltage unbalance. As you all know, there has been growing penetration of distributed energy resources like rooftop solar PV in the recent past. There is some uncertainty associated with the power injection of these resources. And additionally, they're not allocated typically equally between the phases of the distribution grid. So this gives rise to a power quality issue called voltage unbalance. Now, in an unbalanced grid, along with positive sequence components, we also have negative sequence components, which are going to affect three-phase induction motors. And these motors are the most common loads in the grid, and they're also very expensive. So as you can see from the plots here, as the level of unbalance increases, the motors would have to be derated to avoid permanent damage, or else we're going to see an increase in the machine losses. Apart from negative sequence components, we also have zero sequence components now in the grid, which means we have currents in the neutrals that will increase the network losses. So the next question would be, how is voltage unbalance measured? So interestingly, there are three commonly used definitions of voltage unbalance as summarized in the table here. So the true definition of voltage unbalance, also called VUF or voltage unbalance factor, is the ratio of negative sequence or positive sequence voltage. The other two definitions shown here are actually approximations of the true definition, and they use voltage magnitudes only in order to measure unbalance. So the NEMA definition here, which is used predominantly by motor manufacturers, uses line-to-line voltage magnitudes to measure unbalance. It's also called as LVUR. Similarly, we have PVUR, which is phase voltage unbalance rate. It's an IEEE endorsed definition and a guideline for distribution system operators. And here they use phase to neutral voltages to measure unbalance. So what is interesting to note here is that all these three definitions are partially inconsistent. So what this line here is trying to say is, if any operating point satisfies any one of these standards, it doesn't mean it satisfies the other two standards too. So moving on to the solutions to mitigate unbalance that are already existing. So one of them is to allocate the residential loads evenly between phases. But this is done rarely in the year. So for most part of the year, we still have an unbalanced grid. The other option could be to use regulator or transformer taps. But since this involves constant switching action, it might lead to a failure of the equipment. Also, we could add additional energy storage to balance the grid, but that might be a costly option. So what method we use in our research work here is the reactive power control. So most solar PVs are connected to the grid through inverters, which have reactive power capabilities. And these inverters are not always at their rated value. So we can use the reactive power control of the inverters to minimize unbalance. And since we use existing equipment, it might be a more cost-efficient solution. So now I'll move on to the motivation for the work. There has already been some work in this area where the active and reactive power of the inverters have been used to minimize unbalance, but they mostly focus on one of the voltage unbalance definitions. Different from the previous work, what we try to do is have a more comprehensive approach and look at and evaluate how using different definitions of unbalance has an impact when we solve the three-phase optimal power flow problem. We also look at the impact on other power quality metrics like network losses. In order to do this, first we have to set up the distribution grid model with all the major components. And then we also formulate the three unbalance metrics as both constraints and an objective function. Like I mentioned before, we look at other power quality metrics too. One of them is network losses, since it is the driver for cost of electricity. So we calculate the losses by calculating the voltage drop across the branches and the current flowing in the branches of the system. The other power quality metric that we look at is the power factor at the substation that we calculate as shown here. So for a given active power in the system, if the power factor is very low, then the apparent power is high, which means the equipment rating at the substation needs to be higher. This also sometimes means we have larger currents in the grid, so which will lead to higher network losses. So now I'll move on to the formulation that we use for this work. We basically have two main formulations. So on the left here, you see that we minimize voltage unbalance subject to various operational and physical constraints. On the right, we minimize network losses subject to the same constraints as here, but we have an additional constraints on voltage unbalance now. And it should be noted here that in both these cases, we use all three definitions of voltage unbalance for the formulation. Another thing to note here is that we use nonlinear AC power flow equations. And to do this, we model the distribution grid in Julia, and we use IPOpt as the solver to solve the optimization problem. And all the network data that we have comes from GridLab-D. So we benchmark the formulation against GridLab-D. Now I'll just give a brief overview of the distribution system modeling. So we'll start off with distribution lines. Here is a very simple example of a two-bus system. As you can see by the variables listed here, we use polar coordinates. Since we are dealing with an unbalanced three-phase system, we cannot ignore the mutual couplings between all the phases. So the branch admittance matrix is going to look like this. It's a 3x3 matrix where the self-impedance values are in the diagonals and we have mutual couplings on the off diagonals. Typically, distribution grids, the nodes in distribution grids are not three-phase, all of them. Some of them are single-phase or two-phase. So in such cases, the branch admittance matrix reduces in size correspondingly, as shown here. Once we have this matrix, we calculate the overall bus admittance matrix of the system, and we use the G and the B matrices here for our nonlinear power flow equations. The next component is transformer. So here is a single-phase equivalent of the transformer model. The transformer admittance matrix is going to be a 6x6 matrix with 4 submatrices as shown here. The C matrix here is a connection matrix that maps the voltage drop across these coils to the actual node voltages which we have in the optimization problem as variables. And this YPR is a primitive admittance matrix that looks like this. So we have some assumptions when we model the transformer. One of them is we ignore the interface coupling. So that's why we only have non-zero elements in the diagonals of the submatrices and all the off diagonals are zeros. The other assumption is that the self-admittance and the mutual couplings are all of them have similar characteristics and they're all equal to the transformer leakage admittance YT. So that's why we only have ones populated in these matrices. One more thing to note here is the voltage regulator is also modeled as a transformer. The modification here is that we now include the tap ratios, which are held constant. The last component is zip load. So in distribution grids, we have a lot of voltage dependent loads. So we use the zip load model where the constant current and the constant impedance load components depend on a base voltage VB. And of course, we also have the constant power load component. And another thing to note here is that capacitor banks are modeled as constant impedance loads. Due to time limits, I'll just skip the formulation of the objective function and constraints and directly show you the simulation results. So we'll start off by looking at results for the IEEE 13 bus case, which is shown here on the right. So we modified this feeder to add 15 single-phase PV installations. And each inverter here is rated at 50 kVA. And the active power is set to fixed to a constant value such that the overall PV penetration is 35% of the rated load. So we only control the reactive power here. So the active power is set to fixed to a constant value. We'll basically look at 5 problems or test cases. So problem 1, P1 loss, is where we minimize network loss and we don't really look at unbalance. P2 to P4 minimizes the 3 different unbalanced metrics that I talked about before. P5 is where we minimize loss, but we now have unbalance as constraints. And all these 3 values that you see here are the limits specified by the corresponding standards. So I'll start by showing the results of unbalance. On the x-axis now, we have the 3 different unbalanced metrics. And on the y-axis, we have the unbalance in percentage. The green dashed line is the 2% limit specified for VUF and PVUR. The orange bars here are the average unbalance that we see across all 3-phase grids, all 3-phase nodes in the grid. And the blue bar here is the maximum unbalance that we see at any single 3-phase node in the grid. So as you can see, the unbalance limits are violated for PVR, especially in this case. When we minimize VUF, so as expected, VUF goes down, but so does LVUR too. But we see that PVR actually increases compared to P1 loss case. Same is the case when we minimize LVUR. So you can see that these 2 plots are very similar. So that essentially says that LVUR is a good approximation of VUF. Again, we see here PVR limits are being violated. So the best result in terms of unbalance is we get when we minimize PVUR. So we see here that none of the limits are being violated and all of them are below 2%. Same is the case with P5, where we minimize loss subject to unbalanced constraints. We see that all the blue bars are actually touching the 2% limit, which means that the unbalanced constraints that we have are actually binding for this case. Now we'll just look at the results for the other power quality metrics that I mentioned. So now on the x-axis, we have 5 different cases. On the y-axis, so we look at network losses. We look at the substation power factor, and I've also shown the average reactive power injection of all the 15 solar PVs that we have in this system. So you can see for the base case, which is P1 loss, we have loss around 88 kilowatts with good power factor substation and a positive reactive power injection. When we minimize VUF or LVUR, the losses actually increase in the system. So this is because we now have negative reactive power injections. So the inverters are actually absorbing reactive power, and the balance is now coming from the substation, which is why you see the drop in power factor. But in P4 and P5, we actually see the losses don't really increase too much compared to the base case. That is because now we have positive reactive power injections, and so we also see a better power factor at the substation. So now I'll show you results of a slightly bigger feeder. So this is an 820 single-phase node feeder. It's a taxonomic feeder, and we have modified it to add 385 single-phase PV installations, as shown by all the colored dots. The PV penetration level is now around 50%. We have similar 5 cases as before. The only difference here is the base case. So our base case here is just a power flow solution solved using Newton-Raphson. So there's no optimization involved in this case. So I'll start off by showing the unbalanced results. As expected, the power flow solution, we see the unbalanced limits are violated. Minimizing any of the 3 unbalanced metrics actually shows considerable reduction in unbalance, and we also see that there is none of the limits are actually violated. Same is the case with P5. where we minimize loss subject to unbalanced constraints. The difference here compared to the 13 bus case is the blue bars no longer touch the 2% limit, which means now the unbalanced constraints are not binding. So looking now at the other power quality metrics, for the base case, the losses are really high since we don't use the reactive power injection of the inverters. Minimizing any of the unbalanced metrics considerably reduces the losses, but the power factor of the substation goes down because now we have negative reactive power injection for all of the three cases. So the best case for this feeder is P5, where we minimize loss subject to constraints, unbalanced constraints. So we see the lowest losses, and we also see the power factor is better because now we have a positive reactive power injection. So to conclude, the main goal of this work was to look at the impact of how using one definition of voltage unbalance can have an effect on other definitions or other power quality metrics. In order to do this, we set up a flexible model of the distribution grid in a phase by phase frame. So we saw from the results of the two test feeders that they're actually quite different, but some of the main takeaways is that if we minimize one voltage unbalance, it might lead to increase in unbalance based on another standard. And in some cases, it might also increase the losses. What was common in both the feeders is that we observed the lowest losses without any violation of the unbalance limits for P5, where we minimize loss subject to unbalanced constraints. And for future work, one direction would be to look at more numerically efficient approaches when we're trying to solve the three-phase OPF problem, so that it is scalable when we are looking at larger and more realistic distribution feeders. Thank you, everyone, for your attention.
Thanks a lot, Kshitij, for your presentation. It is time for questions. Any questions from the audience? Please, don't be shy. This is the last presentation. I would like some questions from you. Okay, I have some questions. I like very much the analysis and the study that you have done. I have 2 or 3 questions about that. The first one is about the definition that you have used for the power factor in the substation.
Yeah.
Because it is, you have there an unbalanced system, let's say. Is this power factor according to standard, let's say, or something?
I'm not sure if, but because now we have an unbalanced system and the per phase active power might not be the same. So if we are trying to measure the power factor at one single point in the grid, which is 3-phase, then we will still have to use the basic definition, which is the active power or the apparent power. So we sum up the active power and the apparent power at that point. Yeah.
And other question is that all the your control variable is the reactive power of the PV inverter, right?
Yeah.
You have used single phase PV inverters.
Yeah.
Point is, should be possible to use 3-phase PV inverters, but injecting power in an unbalanced manner in order to try to reduce the imbalance, the voltage, inject unbalanced current, say the unbalanced voltage.
Yes, so I think that is something similar to what happens in the 13 bus case result that we have here. So if we look at node 634, it has 3 single phase inverters at the same node, and they're all injecting different active power and reactive power. So yeah, that is the case, sort of case that you're talking about.
But in that case, I think that all the inverters that you are using are injecting the maximum power, let's say, the maximum available power. So you are not using containment, let's say.
Yeah, we don't use contained. Yeah.
I'm trying to say,
Okay.
to do another thing is to substitute this three-phase inverter. Oh, sorry, this one single-phase inverter by one three-phase inverter.
Okay.
Such a way that with an unbalanced current, you can compensate the unbalanced voltages. Are you thinking about that?
Yeah, yeah, that is also one of the things we're looking at in future. So for now, we have always just concentrated on single phase PV. So yeah, we haven't really looked too much into three phase solar in the PV inverter. But yeah, that's a good idea. So that's something we need to look into more.
Any question? Any additional question, please?
There are three questions there.
Three questions. Okay.
Okay, yeah. The first question is, which formulation provides the best trade-off in unbalanced reduction versus computational complexity for larger networks? So I think from what we have seen for large feeders when we have tested this on, so when we minimize PVUR, we have a lower computational complexity since we are dealing with more linear constraints. But VUF and LVUR actually bring more non-linearity when we try to add the constraints or voltage unbalance. So we have more, it is more computationally heavy to minimize VUF or LVUR compared to PVUR. And the next question is, what did you control beside inverters? Yeah, the reactive power of inverters was the only controllable variable that we considered in the formulation. And how do you know the results are not due to local optima rather than the objective scenarios? So because we use nonlinear power flow equations, there is no guarantee that we are reaching the global optimal solution. So all the results that are shown here is when we reach the local optimum. But we could, one of the ways to check if we are reaching at the same solution is for VUF, for example. So it's the ratio of negative over positive sequence voltage. So that makes it slightly non-convex. So we can just ignore the positive sequence and just minimize negative sequence voltage. That also gives a result similar to minimizing VUF. So that's how we know that we are still arriving at the actual local solution, irrespective of what the objective function is. Okay, the next question is, have you considered star delta connections here? Not in the results that I've shown here, but yes, we do have some star delta transformer connections that we have tested in other larger taxonomic feeders, and the formulation works there too. And yeah, there's one more question. Normally, converter is controlled in a three-phase balanced way, but there are some power quality enhancement equipments dedicated for compensating unbalanced grid. Maybe the capability characteristics of the equipment should be considered. Yes, I guess there are other equipments in the grid. Like, for example, we just assume that the voltage regulator taps do not change. They actually might change when we run the OPF. So, but that would make the problem a little bit harder for us to solve because we are going to introduce binary variables in the OPF. So yeah, that is also one of the things we are looking at.
Okay. Thanks a lot for your presentation, Kshitij.
Yeah, thank you.
Yes, some closing words for these sessions. I would like to thank you all for attending this power quality session. Thanks to the speakers for the high quality of the presentations, for sticking to the time, to the allotted time, and also thanks to the attendees for attending this session. Hope you enjoy this PCC the rest during this week, and I hope to see you in the next in the next TCC physically and not in a remote way. So that's all from my side. Any other closing remarks from you, from the attendees? Perfect. So have a nice day. Thanks also to you, Federico. Thanks for your technical support.
No problem. Thank you all for coming.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.